Good morning, everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In the last class, we talked about reduced modulus theory and we also talked about tangent modulus theory. In this session, we'll talk about Shanley's theory. For nearly 50 years, engineers were faced with the dilemma that the reduced modulus theory is correct, but the experimental data was closer to the tangent modulus theory. How was it resolved? Shanley, an engineer working in Lockheed Martin, pointed out that the assumption made in double modulus theory need not be true, and it is possible for the axial load to increase than remaining constant, and eventually resolve this dilemma in 1947. After a thorough experimental investigation on small aluminum columns, Shanley found out the lateral deflection started very near the theoretical tangent modulus load P sub T, and the load capacity increased with increasing lateral deflections Y. The column axial load capacity never reached the calculated reduced or double modulus load P sub R. Shanley developed a column model to explain the observed phenomenon. Shanley's column model. The picture on the left-hand side shows two rigid bars with a deformable cell at the center. It is loaded axially by load P and the length of the column is L. The model is assumed to remain straight until the critical load is reached. It then deflects for a finite distance y0 laterally. A close-up view of the deformable cell is shown here. You can see on the left-hand side, which is on the concave side, it is compressed by E1. On the right-hand side, which is the convex side, it is elongated by E2. It is again pictorially represented. One side, axial compression is taking place, and another side, tensile forces are acting. The axial compression is P1, the axial tension is P2, and you can see the distance between the two is the distance D, and the area is split into two halves, A by 2 on one side and A by 2 on the other side. The distance between the center of the cell to the point of the center of the deformable shape is given as R. R is the radius of curvature. The external moment M external is equal to P into Y0. Using trigonometry, we can see that tan theta naught is equal to Y0 divided by L by 2. The Y0 is actually the lateral displacement at the neutral equilibrium. L by 2 is the distance here, and we see that for small values of theta naught, tan theta naught is equal to theta naught. So, theta naught equal to Y0 divided by L by 2. So, Y0 equal to theta naught into L by 2. So, we can substitute Y0 equal to theta naught into L by 2 in the above equation, which gives rise M external is equal to P into theta naught into L by 2. The external moment M external produces stresses and strains in the deformed shell. The curvature of the shell is calculated as shown below. D equal to 2 theta naught into R. So, phi equal to 1 by R, which is equal to 2 theta naught divided by T. Again, for the larger triangle, we can say that tan theta naught, which is given in the green color, is equal to D by 2 plus E2 by 2 divided by X. Again, for small values of theta naught, tan theta naught is equal to theta naught, and X is given as D plus E2 divided by 2 theta naught. Similarly, for the smaller triangle on the concave side, we have the rose color lines. Tan theta naught is equal to D by 2 minus E1 by 2 divided by X minus D. Again, tan theta naught becomes theta naught. So, we have X equal to D plus D minus E1 divided by 2 theta naught. Equating the right hand side of the above equations, we have D plus E2 divided by 2 theta naught is equal to D plus D minus E1 divided by 2 theta naught. So, D by 2 theta naught plus E2 by 2 theta naught is equal to D plus D divided by 2 theta naught minus E1 divided by 2 theta naught. So, we have D by 2 theta naught on either sides, which can be cancelled. So, we have E2 divided by 2 theta naught plus E1 divided by 2 theta naught is equal to D. From this one, we have theta naught equal to E1 plus E2 divided by 2D. From the definition of strain, we have epsilon 1 equal to E1 by D, where E1 is the strain in the compression fiber, and epsilon 2 equal to E2 by D, where E2 is the strain in the tension fiber. So, this can again be substituted, and we can reduce this equation as theta naught equal to epsilon 1 plus epsilon 2 divided by 2. Y0 we know that is equal to theta naught into L by 2. So we substitute again y naught equal to epsilon 1 plus epsilon 2 divided by 2 into L by 2. So this leads to the expression epsilon 1 plus epsilon 2 is equal to 4 y naught by L. So we keep this aside on the right hand side. So P1 is the force in the compression flange on the concave side, which is given as A by 2 into E1 into epsilon 1. P2 is the force in the tension flange, which is given as A by 2 into E2 into epsilon 2. So M interior is equal to P1 into D by 2 plus P2 into D by 2, which gives rise to P1 plus P2 by 2 into D. So this P1 plus P2 can be substituted from the above equation, gives rise to the value AD by 4 into epsilon 1 into E1 plus epsilon 2 into E2. So by equilibrium, we have M external is equal to M internal. So which leads to the equation P into theta naught into L by 2 is equal to AD by 4 into E1 into epsilon 1 plus E2 into epsilon 2. We know that theta naught equal to epsilon 1 plus epsilon 2 by 2. So when we substitute that, we have P into epsilon 1 plus epsilon 2 divided by 2 into L by 2 is equal to AD by 4 into E1 into epsilon 1 plus E2 into epsilon 2. So this gives rise to the equation P equal to AD by L into E1 into epsilon 1 plus E2 into epsilon 2 divided by E1 plus E2, which gives rise to the equation 1. Now, if the cell is elastic, which is it is still in the elastic range, E1 equal to E2 equal to E. Therefore, P becomes PE. So, PE equal to AD by L into E. If the cell is inelastic, E1 is equal to E sub T, where E1 is the modulus on the concave side, which is equal to the tangent modulus, and E2, which is the modulus on the convex side, can be equal to Young's modulus E or E sub T, which is the tangent modulus. The value of E2 is equal to E or E sub T depending upon whether the strain reversal takes place or not. For no strain reversal, E1 equal to E2 equal to E sub T, which gives rise to the tangent modulus load P sub T equal to AD by L into E sub T. Now we have to derive a generic equation for the load P. Substituting E1 equal to E sub T in equation 1, we have P equal to AD by L into E sub T into epsilon 1 plus E2 into epsilon 2 divided by epsilon 1 plus epsilon 2, which is equal to AD by L into E sub T into epsilon 1 divided by epsilon 1 plus epsilon 2 plus E sub 2 into epsilon 2 divided by epsilon 1 plus epsilon 2, which can again be modified as shown below. We are adding and subtracting epsilon 2 in the first term of the equation, which leads to further simplification and is given as P equal to AD by L into Et into epsilon 1 plus epsilon 2 divided by epsilon 1 plus epsilon 2 minus E sub T into epsilon 2 divided by epsilon 1 plus epsilon 2 plus E2 into epsilon 2 divided by epsilon 1 plus epsilon 2. This epsilon 1 plus epsilon 2 can be cancelled. This can be further simplified as AD by L into E sub T plus E2 minus E sub T into epsilon 2 divided by epsilon 1 plus epsilon 2. When we take E sub T outside, this can be further reduced as P equal to AD by L into E sub T into 1 plus E2 by E sub T minus 1 into epsilon 2 divided by epsilon 1 plus epsilon 2. Substituting E2 by Et is equal to K and epsilon 1 plus epsilon 2 equal to 4 y naught by L. This further reduces to P equal to AD by L into E sub T bracket open 1 plus K minus 1 into epsilon 2 divided by 4 y naught by L. This again can be modified as P equal to P sub T into 1 plus K minus 1 into L epsilon 2 divided by 4 y naught. The P sub T here represents AD by L into E sub T. This becomes equation 2. The ratio K is either equal to unity, where there is no strain reversal, or E by E sub T, where strain reversal takes place on the convex side of the model. It has been assumed that the applied load P increases as the column bends. If it is also assumed that the bending starts at the tangent modulus load P sub T, then P equal to P sub T plus delta P, which indicates P equal to P sub T plus P1 minus P2. This P1 minus P2 can be expressed as P1 minus P2 equal to A by 2 into E1 into epsilon 1 minus A by 2 into E2 into epsilon 2, which gives rise to A by 2 into E1 epsilon 1 minus E2 epsilon 2. E1 equal to E sub t because it is on the concave side, where E2 equal to E or E sub t depending upon whether strain reversal takes place or not on the convex side. So we have this equation further simplified as AD by L into E sub t plus A by 2 into E sub t into epsilon 1 minus E2 into epsilon 2, which again can be further simplified by adding and subtracting E sub t into epsilon 2 and subtracting E sub t into epsilon 2. This gives rise to the equation AD by L into E sub t plus A by 2 into E sub t into epsilon 1 plus epsilon 2 minus E sub t plus E2 into epsilon 2. This again gives rise to the equation AD by L into E sub t plus A by 2 into E sub t bracket open epsilon 1 plus epsilon 2 bracket close minus A by 2 into E sub t plus E2 into epsilon 2. This again can be simplified further. AD by L into E sub t, we take it the whole thing outside the bracket into 1 plus E2 divided by E sub t into epsilon 2. So when we substitute E2 by Et equal to k and epsilon 1 plus epsilon 2 is equal to 4 y naught by L, we get another equation P equal to P sub t into 1 plus 2 y naught by d minus L into epsilon 2 divided by 2d into 1 plus k, which becomes equation 3. So we have two equations for load, equation 2 and equation 3. So now we have to eliminate epsilon 2. So we are actually going to do that by finding out the value of epsilon 2 in equation 2 and finding out the value of epsilon 2 in equation 3. So when we do so, we have P by P sub t minus 1 is equal to k minus 1 into L epsilon 2 divided by 4y naught. This when we further simplify it, P by P sub t minus 1 divided by k minus 1 is equal to L epsilon 2 divided by 4y naught. So we get epsilon 2 is equal to P by P sub t minus 1 divided by k minus 1 into 4y naught by L. The equation 3 again gives you P by P sub t minus 1 equal to 2y naught divided by d minus of k plus 1 into L epsilon 2 by 2d. This gives rise to the equation k plus 1 into L epsilon 2 divided by 2d is equal to 2y naught by d minus bracket open P by P sub t minus 1 bracket close. This can be again simplified as epsilon 2 equal to 2d by L into 2y naught divided by d minus P by P sub t minus 1 divided by k plus 1. Now we have epsilon 2 from equation 2, we have epsilon 2 from equation 3. So we have to equate both the epsilon 2's. We have P by P sub t minus 1 divided by k minus 1 into 4y naught by L is equal to 2d by L into 2y naught by d minus P by P sub t minus 1 divided by k plus 1. This can be further simplified as P by P sub t minus 1 divided by k minus 1 into 2y naught is equal to 2y naught minus P by P sub t minus 1 into d divided by k plus 1. This again can be further simplified. P by P sub t minus 1 divided by k minus 1 is equal to 1 minus of P by P sub t minus 1 into d by 2y naught divided by k plus 1. This can again simplified as P by P sub t minus 1 into k plus 1 divided by k minus 1 is equal to 1 minus P by P sub t minus 1 into d by 2y naught. On further simplification, we have k plus 1 divided by k minus 1 is equal to 1 by P sub t minus 1 minus d by 2y naught. Then we have k plus 1 divided by k minus 1 plus d by 2y naught is equal to 1 by P sub t minus 1. So we have P by P sub t minus 1 is equal to 1 by d by 2y naught plus k plus 1 divided by k minus 1. We can take the minus 1 to the other side and we can also further simplify it, and hence we get P equal to P sub t into 1 plus 1 by d by 2y naught plus k plus 1 divided by k minus 1. This becomes equation 4 and this is the Shanley's equation. So the Shanley's equation actually has a component plus 1 by d by 2y naught plus k plus 1 divided by k minus 1, which is multiplied with P sub t. So to begin with, the minimum value of load is P sub t. The maximum value depends upon the value of k in this equation. So here k equal to E2 by E sub t. Since E is always greater than E sub t, we also know that E sub 2 is greater than E sub t. So E2 by E sub t is greater than 1, which indicates that the minimum value of k is 1 and k can be greater than 1. So when k equal to 1, what happens is that the term on the right hand side, the second term within the brackets, is actually 0. So P becomes P sub T. So when we plot the normalized load versus deflection, the x-axis y naught by d and the y-axis is P by P sub T. We have, for k equal to 1.0, we have a very straight line, which is P equal to P sub T. For k equal to 1.5, we have an orange color curve, which is actually increasing with y naught by d. Similarly, k equal to 2.0, we have another curve on top of that, k equal to 2.5, and k equal to 3, and k equal to 3.5, and k equal to 4. We can see that as k increases, there is marginal increase in the load carrying capacity. From the plot, it can be observed that the model begins to bend at the tangent modulus load P by P sub T equal to 1 at y naught equal to 0, which indicates y naught by d is equal to 0. As y naught increases, the variation of P depends on the value of k. The ratio k is either equal to unity, where there is no strain or no strain reversal takes place, or E by E sub t, where strain reversal takes place on the convex side of the model. When no strain reversal takes place, k equal to 1, so P equal to P sub t. However, bending at constant load produces strain reversal. The assumption of no strain reversal thus leads to inconsistent results and must be discarded. Now, assuming that the strain reversal takes place, k greater than 1, it can be shown that P increases and approaches PR, which is the reduced modulus load, as the deflection y naught becomes large compared to d, that is y naught by d tends to infinity. In the reduced modulus theory, the assumption followed is that the axial load remains constant. That is delta P equal to P1 minus P2, that is equal to 0, which implies P1 equal to P2 and E1 equal to E sub t, which is on the concave side, and E2 equal to E on the convex side, where strain reversal takes place. So, A by 2 into E sub t into epsilon 1 equal to A by 2 into E into epsilon 2, which indicates E sub t into epsilon 1 equal to E into epsilon 2. So, epsilon 1 equal to E by E sub t into epsilon 2, which indicates epsilon 1 equal to K into epsilon 2. Now, we know that epsilon 1 plus epsilon 2 equal to 4 y naught by L. We have K into epsilon 2 plus epsilon 2 equal to 4 y naught by L, which gives rise to the value epsilon 2 equal to 4 y naught by L into 1 by K plus 1. So, substituting this value in equation 2, which is P equal to P sub t into 1 plus K minus 1 into L epsilon 2 divided by 4 y naught, we have PR equal to, which is the reduced modulus load, is equal to PT into 1 plus K minus 1 divided by K plus 1. This becomes equation 5. Substituting K equal to 2.0 in the above equation, we have P equal to P sub t into 1 plus 1 by 3. Basically, 2 minus 1 is 1 at the top and 2 plus 1 equal to 3. So, P equal to P sub t into 1 plus 1 by 3. So, we get P by P sub t equal to 1.33, which is plotted on the curve on the left hand side. Equation 4 is P equal to P sub t into 1 plus 1 by 2 y naught by d plus 3. Now, as y naught by d tends to infinity, we have P equal to P sub t into 1 plus 1 by 3, which indicates P by P sub t equal to 1.33. This proves that the Shanley's curve approaches reduced modulus load when the deflection y naught becomes large compared to d. So, what are the observations from this one? Bending begins at the tangent modulus load and progresses with increasing axial load. As the lateral deflection becomes large, the axial load approaches the reduced modulus load. The most important difference between an actual column and the model is that the E sub t, which is the tangent modulus, decreases with increasing compressive strain in the actual column, whereas it was assumed to remain constant in the model. The left-hand side shows the bilinear stress-strain relationship. If the increase in E sub t is considered, it will follow the dotted line as shown in the plot, which is the actual stress-strain relation. The maximum load lies somewhere between P sub t and P sub r. Although there is no strain reversal at the instant that bending begins, strain reversal does occur as soon as the bending deformations are finite. Now let's compare all the theories. We have the tangent modulus theory, we have the Shanley's theory, we also have the double modulus theory. We know that the tangent modulus theory underestimates the strength, the double modulus theory overestimates the strength, and the Shanley's theory is between the two. So if you plot a graph with load on the y-axis and the lateral displacement on the x-axis, we have Euler theory, reduced or double modulus theory, and tangent modulus theory. We can see that the Shanley's theory is between the tangent modulus theory and the reduced modulus theory. So the Shanley's theory starts with the tangent modulus theory and approaches the reduced modulus theory depending upon the lateral displacement. So for design purposes, it is better to follow tangent modulus theory. Note, all these theories were proposed based on aluminum columns/models. However, for structural steel columns, we need to take the residual stresses into account. We will continue our conversation on this column theory with taking into account residual stresses in the coming classes. Thank you very much.